Hi everyone, my name is Arya Tanmay Gupta and I will be giving a presentation on the article Burning Grids and Intervals. I will start by defining graph burning, then I shall discuss burning of a path. After that, I'll discuss burning of interval graphs and how burning of the concept related to burning a path is related. It reduces to NP completeness of burning interval graphs. Then I shall discuss burning of grids, and finally I will conclude the presentation. Graph burning is a discrete time process in which at every time step an unburnt vertex is burned from outside, and then the fire spreads from the vertices which were burning up till the last time step to the vertices neighboring to them. As shown in this figure, this is the time step 0, no vertex is burning. At time step 1, let's say we burn the vertex R. At time step 1, the fire will not spread because at time step 0, no vertex was burning. Let's say at time step 2, I burn the vertex Q. Now the fire will spread from the vertex R to the vertex P. Let's say at time step 3, I burn the vertex S and the fire will spread from the vertex Q to the vertex T. Let's say at time step 4, I burn the vertex W and the fire will spread to the vertices U and V. This is one example in which I can burn this graph in 4 time steps. The sequence of vertices that were chosen to be burned from outside are R, Q, S, W. Well, we call such a sequence a burning sequence. Burning sequence is a sequence of vertices which is able to burn a given graph completely. And the burning number of a graph is the least amount of time steps which are required to burn that graph, or equivalently, the least size of the burning sequence required to burn the graph. So, as shown on the figure on the right, we can burn this graph by a burning sequence QVU, and this sequence is of size 3. Well, the burning number of this graph happens to be 3, so the sequence QVU is an optimal burning sequence. There can be other optimal burning sequences as well, but QVU is one optimal burning sequence. Graph burning was introduced by Bonetto and others in 2014, and the aim of the graph burning problem is to burn a given graph in the least amount of time steps. Let's see how we burn a simple path, and this is time step 0. We are going to assume that we are burning a path of infinite length, and we are also going to assume that we are going to place fire sources at a distance infinite from each other. At time step 1, I place one fire source. At time step 2, I place another fire source, and the burning cluster of the first fire source increases by 2 vertices. At time step 3, I place another fire source, and the burning clusters of the second fire source and the first fire source increase by 2 vertices each. And in the fourth time step, I place another fire source, and the burning clusters of all other fire sources increase by 2 vertices each. Here we can see that we are actually obtaining a sequence of odd numbers because every cluster starts with one vertex, and at each subsequent time steps it can increase by 2 vertices, one in each direction. And so since the sum of the odd numbers, consecutive odd numbers, is k consecutive odd numbers is equal to k square, if we are given a path of size p of p vertices, we'll be able to burn that path in root p time steps. This is one example. It's a path of 9 vertices, and we are able to burn this graph in 3 time steps optimally. Now we are going to see how burning of a path gets reduced to burning of interval graphs and other interesting observations. So this is the example that I just discussed. In this example, the first fire source is X1 and its cluster is marked with red. The second fire source is X2 and its cluster is marked with green. And the third fire source is X3, its cluster is marked with black. In fact, the cluster of the third fire source only contains one vertex, which is itself. In this case, the burning clusters can roam around on the path such that the clusters, if um, there is one constraint, if the cluster is shifting itself, the fire source will also shift with the cluster. So at the topmost image, I shifted the green cluster to the left. I shifted the red cluster in the middle. But if I add one vertex to this graph such that I connect that vertex with V8 by an edge, we will have to place either X2 at vertex 8 or fire source X1 at vertex 7, V7. The reason is X2 has reachability 1 and X1 has reachability 2. So these are the only fire sources which will be able to burn this structure, and hence we will be able to burn this graph optimally. Let's start again. This time I shifted the green cluster to the left, the black cluster to the middle, and the red cluster to the right. If I add three vertices to this graph, if I add three vertices to this graph such that those three vertices are connected, each of these three vertices are connected to V2, V3, and V4 respectively by an edge. I will have to place X1 at V3 only because otherwise I will not be able to burn this graph optimally. And so the position of X1 is fixed. And if I place on that graph, if I place one more vertex such that I connect that vertex with V8 by an edge, I will have to place X2 on V8, otherwise will not be able to burn this graph optimally. So the position, since the position of X1 was already fixed, now the position of X2 is fixed, and as a result, the position of X3 is also fixed. Well, here we can see that the path is kind of divided into subpaths of order it's the orders of the subpaths is a sequence of odd numbers, and the fire sources are fixed only because we have added vertices in this fashion. So what we are doing here is we are making comb structures. A comb structure of size k is has a principal path of size k, and on that principal path, every vertex from the second vertex to the second last vertex is connected to a vertex each by an edge. And the comb structure is valid to be an interval graph. It's a valid interval graph. And in the same manner, we can add any number of combs, any size and any number of combs and paths one after the other, and the resulting graph will be a valid interval graph as shown here. So we are going to reduce the distinct three partition problem on burning of interval graphs. The input of the distinct three partition problem is a set X of integers, and the problem is to determine if X can be partitioned into subsets of size 3 each, such that the sum of elements of each subset is equal. There are other constraints associated with the distinct three partition problem, but for our reduction, this description is enough. So for example, let's say that X is 10, 11, 12, 14, 15, 16. We will have to derive n is equal to 2 subsets from X, and the sum of each subset has to be 39. Well, in this example, X can actually be parted into such subsets, which are 10, 14, 15, and 11, 12, 16. We have to take care of other variables as well, a few other variables. So the input x is the input to the distinct three partition problem. N is the number of sets that have to be derived from x. Uh, and B is the sum of each subset that has been derived as distinct as per the distinct three partition problem on X. M is the largest element of X, and K is the difference between M and the cardinality of X. Well, in this case, X is as stated, N is 2, B is 39, M is 16, and K is 10. We also need a set of natural numbers from 1 till M. If, according to this example, Fm is 1, all the natural numbers from 1 till 16. We also need a set of odd numbers, Fm prime, which is all odd numbers from 1, first odd number 1 till the mth odd number to m minus 1. In this example, Fm prime is the set of odd numbers from 1 till 31. Next, we need a set x prime, which is a set of odd numbers corresponding to the numbers in x, to the elements in x. So x prime contains 10th odd number, which is 19, 11th odd number, which is 21, 12th odd number, which is 23, and so on in this example. Y is the set of odd numbers which are present in Fm prime but are not present in x prime. So Y is the set 1, 3, 5, 9, 11, and so on. B prime is the sum of all subsets when those subsets are derived from X prime according to the distinct three partition problem. B prime in this example will be 75. Next, we are going to construct combs and paths. So we need combs of size as per the next m plus 1 odd numbers which come after the elements of fm prime. So we need combs of size 33, 35, 37, and so on up till 65. We also need n paths q1, q2, and so on, where the size of each path is b prime. In this example, the size of q1 and q2 is 75. Next, we need k subpaths q1 prime, q2 prime, and so on, such that they are of size as per the elements of y. So if we look closely here, if and only if q1, q2, and so on, the n paths of size b prime each, they can be divided as per the distinct three partition problem on x prime. We will have obtained combs and paths of size as per each odd number from 1 till 2m plus 1th odd number. We can arrange these combs and paths in any order with one restriction that two paths cannot be joined one after the other. Two combs can be joined one after the other, but between two paths there has to be at least one comb. We call this graph IGX, and this is one example of IGX. Well, we can see that there is a path being induced in this graph, and this path is the largest path of this graph. This is the principal path of this graph, and we call this path pi. And if let's assume that q1 and qn can be partitioned as per distinct three partition problem on x prime, then we will obtain that if we place fire sources on the principal paths, on the principal subpaths, such that we place the ith fire source on the ith largest principal path of uh, when they are divided as per the odd numbers. So we'll get that the burning number will be 2m plus 1. So since the combs are the largest, have the largest principal axis, we have to place the first m plus 1 fire sources on the combs. After burning these combs, we are left with the path forest induced by q1, q2 up till qn, and q1 prime till qk prime. We are going to deal with q1 prime till qk prime first of all. They are subpaths that we can obtain as per the odd numbers in y. So accordingly, we can place fire sources on them such that the burning cluster of the fire source is equal to the number of vertices on the path. If that is not the case, we can replace them and place them such that the cluster size is equal to the number of vertices on the path on which the fire source is placed. This rearrangement will take order of decay time, which is pseudo polynomial in the input x. When we have burned q1 prime till qk prime, we are left with q1 till qn. And by our assumption, if and only if q1 and q1 q2 till qn can be divided as per the distinct three partition problem on x prime, we will be able to burn this graph optimally in 2m plus 1 time steps. So to determine whether such a graph can be burnt in 2m plus 1 time steps is equivalent, equivalent to uh, uh, equivalent to the distinct three partition problem on the set x prime, and equivalently it is equivalent to the distinct three partition problem on the set x. So we have reduced the distinct three partition problem on burning interval graphs. Since the distinct three partition problem is NP complete in the strong sense, we have that the burning of interval graphs is also NP complete. As corollaries, we have that the burning of mastic graphs, permutation graphs, disk graphs, trees, caudal graphs, path forests, planar graphs, bipartite graphs, spider graphs, and forests. Burning of these graph classes is NP complete as well. Next, we are going to study the burning of grids, and we'll start with describing how uh, the fire spreads from one single fire source. So at time step 1, I placed one fire source. At time step 2, 4 more vertices are burned. At time step 3, 8 more vertices are burned. At time step 4, 12 more vertices are burned, and so on. So this is the sequence that we obtained, and as per that sequence, we have that we can burn 2k square minus 2k plus 1 vertices by a single fire source in k time steps. By this property, we have that if we have a burning sequence of length I, we can burn 2i cube plus I upon 3 vertices in using that burning sequence. And as a result, we have that if we have to burn a grid of size L cross B, we need at least L cross B to the 1/3 fire sources to burn that to burn that grid completely. So based on these observations, we have an approximation algorithm as follows. Given an L cross B grid, divide that grid into subgrids of size L to the 2/3 cross B to the 2/3. As a result, there will be roughly L to the 1/3 to cross B to the 1/3 such subgrids. We are going to put fire sources in each subgrid such that we place one fire source in the radial center of the subgrid, each subgrid. Um, If the grid is a square grid, L cross L grid, we will be able to burn that grid using this process in 2L to the 2/3 plus 2L to the 1/3 plus 1 time steps. And if the size of that square grid is greater than or equal to 403 cross 403, we'll be able to this we have obtained two approximation algorithm for burning square grids. Now I conclude this presentation. Um, Burning of we have observed that burning of several graph classes is NP complete, even for those graph classes where solving of other NP hard problems is polynomially possible. Um, Other graph classes can also be studied from the perspective of graph burning, and it is still an open question whether burning grids is possible in polynomial time. This ends my presentation. If there are any questions, I will be happy to answer. Thank you.